Hi and welcome. In this video we're going to dive deeper in the geometries after the box, so we're going to learn how to use the sphere and cylinder structs in RhinoCommon. So if we go to the RhinoCommon API website, we can select the Rhino, the geometry namespace, and if we go, let's start with cylinder at first, and in this case we find it here. And if we go to a cylinder, we find that it's a struct and it's a pure geometry namespace, and it's not inherited. It does not inherit to any other classes or structs. So a cylinder can be constructed using a base circle and a double height, or just a base circle. So it goes with infinite height, and it has some properties like getting the axis direction of the cylinder, unsetting the cylinder, getting its center, its height 1 and height 2, and check if it's valid. We can get the radius and the total height of the cylinder. We can get the circle at some point of the cylinder, let's say on its height. So if we want it to get the circle at z coordinate 1, it gives us this circle. We can get a line at it. We can transfer it to a B-rep or to a NURBS surface or to a rev surface. Let's check how is it done. As we see, it's not a really complex geometry, so let's try it. At first, let's create our C# script, and here all we have to do is to type cylinder A equals a new cylinder. And here we'll have to stop because it requires something that we didn't learn before, but it's it could be initiated by logic as we understood the lines and so on. We can find a circle struct, I think, here, and we can construct a circle using an arc, using a radius, and it will start at the center, at the origin exactly, or we can use a plane and the radius, or a point 3D center and the radius. We can create it in every way possible to create a circle. So we can here write a new circle that starts with the origin, let's say, and is let's just write here radius and take it from the inputs of the C# script, and let's add a height and call it height. Okay, and here we will say that A equals cylinder A. But now we need add the inputs here. So our inputs are, okay, so when I close this, we'll have to do this again. I'll pause the video and do it again. Yeah, so here we are. All we have to do now is to add our radius and make sure that it's a double, and add our height, and again make sure that it's a double. So if we run our script now, it turns nothing because we didn't add a radius. Let's say it goes from 1 to 5, and the height to be going from 1 to 10. Okay, and now if we do this, it will give us a cylinder that has a height of 1 unit and a radius of 1 unit, so a diameter of 2. We can now control our cylinder easily. And if we want to get a circle at the cylinder, all we have to do is, so of course it will have a circle data type. So circle at cylinder A equals cylinder A dot circle at, and we'll choose this and we can type the double we want, or we can just, let's write len param here, and we will assign it to the output B, which will be circle at cylinder A. And if we run this, we need to copy the line, the linear parameter here, and add it to the inputs, and we need to add a B, and we have a problem in this code. So it says, yep, we didn't make this as a double. That's our problem. Okay, so we can copy the height here, but start it from 0 to 10, to the maximum height we can have, which is 10. And if we add this to the linear parameter, we find that we can get the circle from 0 to 10. So the same exact way happens with a sphere. Let's try to create a sphere instead of a cylinder. And in this case, it will probably need a plane and radius, or a point 3D, a center and a radius. And it's still a struct, and it's a Rhino geometry under the Rhino geometry namespace. It's almost the same properties: bound box, bounding box, unset, center, diameter is valid, radius. Those are the main properties that we'll use probably. It has some methods so we can fit a sphere to some points. Remember, constructing the box, the minimum box that contains some points, it was a constructor, but in the sphere it's a method rather than a constructor. So if we want to fit a sphere to some points, all we have to do is draw our points, let's say add them to a list, or identify them as a list in the axis in the input of the script, and use the method fit sphere to points. We can get the closest point, we can get the normal at a certain place on the sphere, or a certain location on the sphere. We can get a point at the sphere, we can rotate it, we can translate it. And this is actually different because in most of the classes and structs that we've learned so far, we didn't have a rotate or a translate method, but it's purely in the geometry, in the geometries. It works with the geometries, like the sphere, like the box, like a lot of things, but it still has the transform method. So anyway, we can do a lot of things. Let's try some of them. Let's try constructing a sphere. So let's just hide this one and create a new sphere. So basically we'll write sphere, the struct's name, and call it sphere A equals a new sphere. And let's check what it needs. A center, let's say it's the origin, point 3D dot origin, and a radius, which will be radius, and we'll get it from the input, and A equals sphere A. So if we run this and close here, we need to change the input name to radius and make sure that it's a double. Now it works, and if we add some slider here, we can control our sphere. So it starts from 1 to 10 as a radius. And let's try to get, or to do some methods on it. We can get the diameter if we want by just writing B equals sphere A dot diameter, And let's check. I don't think the brackets are necessary. Let's try it. Yeah, it's not necessary. If we add here, of course, if this is 10, then the diameter will be 20. Okay, we can try a lot of other things. Let's check here. We can find the closest point. So if we have a point somewhere and let that be changeable, meaning if we just draw a point here and we add it to a test point input, and we'll make sure that this test point is a point 3D object and connect it here and set it. So now we have this point and we want to know which point on the sphere would be the closest point to this point. And to calculate this, we have to do the following. We'll have to say, of course, we need a point, so it will have a point 3D type, and see point at sphere equals sphere a dot point at oh no, sorry, sphere a dot closest point, right? And here it needs the test point, so we'll just write the test point that we added, and we'll add a final output called point at sphere. And if we run this, it won't work. We need to add a C output, and here we go. So this is the closest point on the sphere to this point. If we move this point, we'll find that this point, of course, changes. Again, what else can we try? We can get a normal, but it's a vector. Okay, and we can rotate. Let's try the rotation and translation. So they are not static, so we and it's a bool, if you see here, so it just moves the sphere, and it's not necessary to store it in another, or you even can't store it in another sphere, because this is a Boolean type. It does not return a sphere. So let's try it, and here we can say sphere a dot translate, and all it does need is a vector. Okay, so we can create a new vector, or we can add a vector. So we can say here vector, and if we run this, it won't work. We need to add a vector here and call it vector, and with a type and vector 3D. And if we run this, it works now, but it doesn't move because the vector is 0, 0, 0. So we need to add a vector. Let's construct a vector xyz and connect it here. Or we can, of course, type vector 3D vector a equals new vector 3D and add it. Anyway, we just want to move it in the z direction with 10 units. So we'll connect this here, and our sphere moved to the z direction. Okay, here is a hint. If we translate the sphere after getting the closest point, the closest point falls outside the sphere. Why? Because it works as if the sphere is on the 0 location. Here now the point is exactly on the sphere, but if we move it, we find that we got the point before translating the vector. And this is very important, because in programming the compiler goes line by line, so it checks what did you do first. At first I got the point and I stored it as a point in somewhere in some location in the memory, and it stored it and saved it, and it output our point. And after that I translated the sphere, so now the point of course doesn't fall on the sphere. This is a really important hint, so the order of the lines matters. Okay, at last, I'm not going to code this, but let's say that we have other geometry, other primitive geometries that exist in the RhinoCommon, including the cone. So you can create an ellipse if we're talking about lines, so you can create an ellipse, you can create an arc as we saw. All you have to do is just check what arguments you need to add to the brackets of the constructor. And of course we have a cone here. You can check a cone. All it needs is a plane, a height, and a radius, and it will give you the cone. And you can get its height, its axis, its base point, its plane, and etc. And the method here just are not really interesting, because all you can do is turn it to a B-rep or an up surface and so on, or get some angles and so on. So that's it for this video. I hope you find it interesting. If you have any questions, please write them in the comments. And if you like the contents of this playlist, please subscribe and like the video. Thank you for watching, and see you in another video.